instructions to lead a discussion on quantum information in AdS CFT. So I do intend for this to be a discussion. So I'll write out a sort of an outline. Is there some?
I'm just moving the chairs out of the way for you.
Oh, so I don't.
You don't stumble.
Die. Yeah. Thank you. So yeah, I'm going to write out an outline, but I'm totally happy just to be derailed and for this to turn into a discussion. So that's the first caveat, and the second is that I am definitely not an expert on all things related to quantum information and AdS CFT. Very far from it. I mean, there are certain specific things within this area that I happen to have worked on, and I think I know something about, but a lot of it, it's just I've read papers or I've sat in on talks, and I haven't necessarily thought deeply about it. So I'm very happy to have a discussion where I learn something about this stuff. Okay, so so let me just give one reference, which is just sort of an entree into the literature, which is a recent SNOMAS paper by Busso and friends, which I recommend. If you're interested in seeing the current state of the art, it's a good place to start. It's not pedagogical, but it gives all the citations and it kind of tells you the current state of the art. So I think it's useful. Okay.
Does V1 give all the citations or V2?
Yeah, there's definitely more in V2. Funny how that works. So I mean, the basic question here is, what have we learned about AdS CFT? From quantum information, and maybe more importantly, what do we hope to learn in the future? I suppose one could also ask the converse question: what have we learned about quantum information from AdS CFT? And that's definitely that's significant. I mean, there's very significant amount of work in, for example, quantum error correcting codes, quantum teleportation, that has come out of tensor networks, that has come out of AdS CFT. But I'm presuming for this audience, our goal is more to learn about AdS CFT. So that's kind of the direction I'm gonna go with. Plus, I just am not very knowledgeable, honestly, about that at any kind of technical level. Okay, so the structure, first of all, I'll try to somewhat define in a very loose way what is this thing anyway, and then I'm going to start with something negative, which is what aspects of AdS CFT has quantum information so far not had much to say about. And I just want to get that out in the open, because I think it's important, and I think it's interesting, and I think it's, it's a target maybe for the future. And then, so then we'll switch back to the positive. So far had something sharp to say about. So I'm going to divide the positive things into two sectors. So something sharp, and then something in here vague or speculative or not yet fully formed, not yet well understood. I mean, not that everything in here will be completely well understood, but I think there is a distinction between the things that we have something sharp to say about and the things that are promising ideas. And I think that's an important distinction, which is not always made. I think people can obviously disagree about where things fall in these three, and I'm happy to discuss it. And then, of course, also, I'm not trying to be comprehensive. There's lots of other things we can talk about that I won't bring up. And so just feel free to bring up anything you want to. Okay, so, for me, so far, I mean, I could try to give some grand philosophical definition of quantum information, but I'm not going to. Instead, I'm going to define it as a list of buzzwords. So basically topics that somehow people seem to think of as being quote-unquote quantum information. So I don't think it's, a very well-defined, well-delimited set of ideas, and that's fine. But in practice, for AdS CFT, as opposed to, let's say, the endeavor to build a quantum computer or something like that, it has entailed mostly the following things. So, of course, entanglement, and including entanglement entropy. So this is the thing that with Ryutake Yanagi kind of kicked everything off. This word complexity, which is, perhaps the slippiest, most slippery word in all of physics, if it is even a word in physics. Then you have things like teleportation, which is a communication protocol. I don't know. Then there's, in quantum error correction. And then there's some things, I don't know if they're quantum information or not, but anyway, tensor networks. And then chaos, I guess, I'm not sure if chaos is really like, I don't know, many-body. I mean, there's, some of it is more about many-body physics than really quantum information. But anyway, I mean, these are the buzzwords you hear at conferences, the kind of conferences that have quantum information in the title. So that's my definition of what quantum information is. I don't know, anything else I should add to this? Anything glaringly missing from this list? Okay, so like I said, I think it's important to get out into the open some things that, perhaps somewhat strangely, especially from the point of view of the rest of this conference, that's really focused on the microscopics of AdS CFT, and, supersymmetry and SU22/ whatever, and this kind of thing is just, has not at all appeared on the, in this set of topics. So the compact dimensions. And let me just say something right off the bat about this. So, I mean, you will almost never hear the existence of the S5 mentioned in any talk that has any of these buzzwords in the title, in my experience. And if you hear somebody talking about something like, and I'll talk a little more about this later, but, we can reconstruct the bulk geometry by looking at the areas of Ryutake Yanagi surfaces and stuff. Just ask the person, well, the bulk geometry, can you get the S5? Do you see the S5? And the answer is no. It's completely invisible to, essentially all of these things, right? I mean, I find that extremely striking given that, the S5 is just the same, it's not microscopic, it's, it's the same size as the AdS5, so.
Not at the boundary.
What?
Not at the boundary, right? It's very small at the boundary compared to the field.
Yeah, well, we're not just interested in.
But you're interested in the
I mean.
Constructing the bulk, yeah.
So this is one thing, and then, I mean, I think an interesting question that I think all of us would agree is an interesting question is to what extent supersymmetry is really essential to AdS CFT. All the examples we know explicitly are supersymmetric, but maybe that's a lamppost thing, etc. So that's a very old debate, and I don't know if it's a useful input to that debate or not, but no aspect of supersymmetry has ever appeared in any work on quantum information that I know of in AdS CFT. I mean, I guess there's something called supersymmetric Renyi entropies, which is the closest you can come. Yeah. Okay, and then another big thing totally missing, and again, I don't know whether this is actually, maybe this is a deep statement, or maybe it's just a sociological statement, is basically, strings, or anything about the UV completion of the bulk theory. So all of the work is at the, so it basically, essentially all of the work already assumes bulk locality. And it works, with classical or semi-classical gravity. And seems to be totally independent of the UV completion. And so again, I don't know whether that's just that people haven't thought about it. I mean, I know it's not just that people have thought about it to some extent and haven't come up with anything nice. So I don't know if that's just that we haven't been smart enough, or whether this is a deep statement that somehow at some level, the UV completion is irrelevant to AdS CFT and you just shouldn't worry about it and so on, that it's kind of like, that like, in some sense, understanding AdS CFT kind of factorizes into, understanding the UV completion of quantum gravity and then understanding holography. And these two things like have nothing to do with each other. That would be a very strong statement that I'm sure people could, disagree with, but so far it's looked like that for this kind of work. And so all of these things are important issues for future work. So I think if you're listing like important open problems for people who are interested in applying quantum information theory to AdS CFT, this is, these things are really big open problems, okay? So, I don't know, before I go on, any comments?
So these tensor networks that people talk about, are they supposed to be a cartoon of the UV degrees of freedom?
That's very unclear. I think it's not yet clear whether they are a cartoon of microscopic AdS CFT or sort of at the AdS scale AdS CFT. And no one has really convincingly given a model which looks anything like string theory or even gives any kind of real bulk locality at the sub-AdS scale using tensor networks. I mean, people have tried. Yeah. So I'm happy at any point to come back around to these, and if people have ideas for like, oh, have you thought about this? As I talk about the positive things, I think that would be very interesting.
Okay. Something, sort of related to this. You would think that if people are trying to apply quantum information ideas to black holes, then the microstructure of black holes, which invoke many of these, which really need, say, compact dimensions, or it needs stringy completions, these should play a role, but it hasn't. So firstly, that discussion itself really doesn't use so much the fine-grained microscopic understanding of black holes. Is that
right? Yes. It's. One answer is to say, look at the Bekenstein-Hawking formula. That shows that there's this universality that just from semi-classics you can get the entropy. It doesn't matter what your UV completion is. And then what we've learned is that for many purposes that continues to be the case even if you follow the evaporation of a black hole and look at what happens to the microstates and so on. You don't which is surprising, right? Because you'd think, well, don't you have to know the microstates to know what happens to the microstates? But so far it doesn't seem to be the case. So that universality seems to hold, in quite a strong sense. But I don't think we understand why. I mean, it's not at all clear. It's not clear why this should be the case. So presumably, in order to understand why it's the case, you do have to know something about the microscopics. Yeah.
But many of these things actually just come from semi-classical gravity path integrals, right?
Yeah, and I think, okay, they come from semi-classical gravity, and the path integral is one tool you have to understand semi-classical gravity, and it seems the the semi-classical gravity path integral seems to be much more powerful and much more knowledgeable, than you might have expected. And of course, I mean, we already knew that from, there's the very old, from the 70s, Hawking derivation of the Bekenstein-Hawking formula from the gravitational path integral. And if you spend too long thinking about that derivation, you don't understand at all why it should work. But the path integral does seem to be like much more powerful than you would normally think. But on the other hand, I mean, I do want to caution that, I mean, I don't necessarily view the path integral as the be-all and end-all. Like, you can get almost everything that's been done without, if for some reason you don't believe in Euclidean quantum gravity, you actually don't need it for, most of this story, But we have learned that it seems to be very, very well behaved. In fact, I mean, so one of my points in 4 was going to be, the gravitational path integral is very well behaved. It's a somewhat fuzzy statement, but it's something that we've learned. Okay, so let's turn to more positive things. And mostly I'm going to talk here about basically things that we've learned following from the RT formula. And then, I mean, I'll just say, I'm not sure I really want to talk about them because it's not, but unless people want to. But yeah, let me just say, so this is sort of one thing. Another thing, so this is a very big topic. So that the bulk in AdS CFT can support teleportation. In other words, there's a teleportation protocol which transmits information through the bulk. And then another thing which I have no particular expertise in is the fact that gravitational theories are maximally chaotic. So these are all sharp things. In particular, this one you can calculate a Lyapunov exponent. You can show that it saturates a bound. You're actually doing a calculation. It's not a cartoon. Here again, there's a protocol where you can have two boundaries, two field theories that are in an entangled state, which is the starting point for quantum teleportation. It's just, Alice and Bob share an entangled pair of qubits, and then they do some protocol, and they can, Alice can send a state to Bob, a quantum state to Bob.
Protocol is classical communication?
The protocol involves classical communication. In this case, the protocol involves coupling them, so it's not quite classical communication. I mean, maybe it can be said in that way, but it involves adding, so far these are not interacting, but you add a double trace deformation that makes them interact, that couples them, and then you show that in the bulk, now there's a wormhole that opens up that you can actually send stuff from one to the other.
So is that supposed to be surprising, that I get two field theories that were non-interacting, I make them interact and I can send something from one to the other because of the interaction?
No, I mean, at some level, it's not, the fact that you can do that it's not like there was a paradox that this solved or something like that. The thing that's surprising is that the bulk, is that there's a gravity dual.
You do it so nicely through the bulk, yes, in such a non-violent way.
Yes.
Because it has a description in terms of a wormhole? Or?
Yes, there is a physical wormhole that grows as a result of this double trace deformation that you can send a person through, from one to the other.
He'll live all the way.
Yes. Yeah. So that's the part which is, I mean, of course, the fact that if you have two systems that are entangled and you make them interact, then of course they will interact. That's not surprising. Yeah, I mean, in some sense, yeah. The fact that this is possible is not surprising. The fact that it has the point here is that it has a nice holographic description. That's the thing which is of interest.
Okay. And I suppose the fact that you can take this guy and send him without
getting scrambled.
Yeah, that sounds sort of interesting, I suppose.
Yeah. No, it's how, it's semi-classical, the things in the bulk, it respects bulk locality. It's not some, it's a process you can understand in a completely semi-classical way in the bulk.
You send Encyclopedia Britannica, not its burnt ashes.
Yeah, exactly. There's no decoding or whatever you have to do, so that's the interesting part of this. But I think I'm happy to talk more about these, but I think I'll focus, at least for what I'll sort of talk about here, more on A. Recently over T, I asked Marcos a question about RT and Gokuravatha duality, and he gave me an answer that I haven't heard in a long time. He said, "What is RT?" So that was a breath of fresh air for me. So let me be explicit here, not make assumptions about what people know. And he also asked me, why are these entanglement entropes interesting? So that's another question I haven't heard of. Okay, so actually, so what I'm gonna jump right to this upgrade of RT. So I mean, for those who care, this one is for static states. It was the original one, and then this is the fully covariant. So I think we're more interested in the covariant one, but I mean, often people just refer to them both as RT or whatever. The task is to evaluate the entanglement entropy. So given a state rho, let's say on a bipartite system, the marginal, the reduced density matrix is what you, a complement, is what an observer in A can see, and the entropy, as always, is the Barnolian entropy. Okay, and then we have this. So I mean, one thing to know about this is that in a relativistic QFT, it depends. In a QFT, we would normally take A to be a spatial region. But then S of A depends only on its causal domain. Okay, so if my space-time is this, and my region is my spatial region is here, then it has a causal domain, and then any other, A prime that has the same causal domain will have the same entropy. Okay, and the HRT formula says that you compute this in terms of the area of a bulk extremal surface. Okay, so And so a couple of comments. So first of all, there's going to be corrections, which I'll discuss in a second. Second, this area is with respect to the Einstein frame metric, which, right. And third, what the heck is M sub A? So M sub A is, this is going to be a little long, minimal, extremal, space-like coordination to surface in the bulk, which is space-like homologous okay, that's a lot of words. So I assume space-like codimension 2 surface in the bulk is okay. Extremal means it's extremal against variation. It's extremal to first order in its area against variations. So another way to say that is that it's the trace of the extrinsic curvature is 0. So the extrinsic curvature vector, or trace of the extrinsic curvature vector, K mu is 0. And another way to say that is that the expansions, so it's a space-like codimension 2 surface, which means that locally it has two, I mean, if I look at its normal plane is a two-dimensional Minkowski space. So if this is a point on the surface, then it has, and this is and the blackboard is the normal plane, then it has these, two normal directions, and each one has an expansion. So if you send light rays from the surface in one of these directions, initially the light rays will be neither contracting nor expanding. Okay? So theta, so the expansion equals 0 in both null normal directions. That's what extremal means.
Sorry, I'm going to embarrass myself, man. Extrinsic curvature is del mu n nu, right?
So
symmetric.
This is codimension 2, so the extrinsic curvature has an extra index. The extrinsic curvature tensor has 3 indices. Two of those indices are tangent indices, and one is a normal index. And here I'm tracing over the tangent indices, and I'm left with the normal. So this mu lives in this normal plane.
Okay, I would have thought 2 were normal and 1 tan. Del mu n nu, and there are 2 n's, right?
Yeah. So you have.
Oh, but one of the it's going to be. Sorry, please go.
There's an index. So yeah, I mean it. So you have an n. Let's call this a normal direction and use mu for. So then I have 2 normals, as you say.
Yes.
And it's a vector, and it has a covariant derivative tangent. So I mean, yeah.
Okay, thank you.
This is K. Okay, now working our way backwards here. Actually, no, let me proceed in this direction. So I've just defined extremal space-like codimension 2 surface in the bulk, space-like homologous to A. Okay, so that means that there exists a space-like or achronal codimension 1. I mean, it's a bit redundant, but I'll just say hypersurface. Whose boundary, so let me call it R sub A, such that the boundary of R sub A is A union M sub A. Okay, so let me do a picture. So here's my A, that's my A on the boundary, and then in the bulk we have our M sub A, And there has to be some codimension 1 space-like surface, hypersurface, that interpolates between A and M sub A. Okay? This, obviously in a simple setting like the one I've drawn where there's no interesting topology going on, I could have just said it's anchored on the boundary of A. So that's implied by this. So it's anchored, M sub A is anchored on the boundary of A, which in this cartoon are these 2 points. Okay, but of course when you have something non-trivial going on topologically, then this is not a sufficient condition. This is a much stronger condition. Okay? Space-like homologous, it's important that this interpolating thing is space-like. Okay, and let me just give one example where that, because people rarely bring it up and it's a little bit of a technical thing, but I feel like I might as well just say like why we care that it's space-like homologous and not just homologous. And especially because I actually think that there's some interesting math that hasn't been fully explored in terms of, a generalization of your normal notions of homology and so on in this Lorentzian setting where you start to put these conditions. So anyway, the example that I'll give is an extremal Reissner-Nordstrom black hole which has 2 boundaries, and it has a time-like singularity. And then it has further, if you continue, it keeps going, etc. And it has these horizons, and then it has this outer horizon, and then it has this inner horizon. Okay. Now, and now what I'm going to do is I'm going to take my region A to be, try to be consistent with the colors, to be an entire boundary. Okay. And by the way, its Cauchy development is, of course, this entire. So A is a Cauchy slice of the boundary, you might have. So in this outer horizon and the inner horizon are both extremal. Okay, and so you might have thought that either one was a candidate to be the HRT surface. This thing is what we call the HRT surface. Okay, but in fact, the inner horizon is not a candidate because it's not. It is homologous to A, but only via hypersurfaces that are not everywhere space-like. Okay. Okay. So already this extremality condition means that there will typically be at most a discrete number of such extremal surfaces. In other words, the number of equations that you need to solve to find an extremal surface is equal to the number of functions you're solving for. So typically you would expect, a discrete, in generic situations, a discrete set of solutions, and if there are more than one, then you're supposed to just pick the smallest area one. Okay?
Sorry, and extremality, that extremality condition, does that mean that local variations of the area vanish?
Yes, to first order.
So that's saying these are local extrema and you pick the minimum.
Yes, exactly. And what typically happens is that basically the surface you find will be a saddle. Okay, it's not going to be I didn't say it's a minimum, I didn't say it's a maximum, it's not going to be either one, because if you take the surface and you wiggle it up and down in the time direction, you will reduce the area, and if you wiggle it back and forth in the spatial direction, you will increase the area. So, you already know it's going to be a saddle, okay? And actually, if you look at this guy is a little bit, which we ruled out on the basis of the fact that it wasn't space-like homologous. This guy is smaller than this one. And so if you didn't have that condition, you would actually have picked this one to give you the entropy. Whereas we know that, with Bekenstein-Hawking, you're supposed to take the outer horizon. That's the fact that there's some inner horizon or whatever is going on inside the black hole, you're not supposed to care about, okay? But also I'd like to point out that this inner horizon has a funny feature that its area increases if you move it in the time direction and decreases if you move it in the space direction. Okay, so now that we have, so you see that the definition here builds into it the existence of this R sub A, which suggests that this R sub A probably has some physical meaning, okay? And indeed it does. So, but again, we have to talk not really about the surface, but about its causal domain. And so its causal domain, its bulk causal domain, is this famous entanglement wedge. So the bulk causal domain of R sub A is the entanglement wedge. And actually I don't know if there's, let me make sometimes it's called like this. Okay, and it's a wedge, you see it's a wedge. Okay?
Sorry, R sub A was the manifold that went from the...
Yes, R sub A is the hypersurface. I think hypersurface is the automatically codimension one, right? Is the hypersurface that interpolates between A and M sub A, and its causal domain in the bulk, which is like this thing, is the entanglement wedge. I can do I'm not great at 3D drawing, so just do another cartoon.
And because it needs to be space-like, its causal domain doesn't depend on which one you choose, right?
Right, so this is, I guess not being consistent with the subscripts anyway, everything, but, right, so now there's actually some questions you can ask here. One question you can ask is, does this exist? Because otherwise, what are you going to do if there is no such surface? Another question you can ask is, does the value of S of A or even M sub A depend on my choice of A for a given causal domain? In other words, questions. Does M sub A exist? Does M sub A prime equal M sub A? Now, so if I have an A prime, it's going to have a different R, and that's fine, but you would expect it to have the same entanglement wedge. So is the entanglement wedge of A prime equal to the entanglement wedge of A? Okay, those are a couple of important questions that this formula raises. And it becomes even more interesting when I make the following claim. So I think, the next thing I'm going to say, I think is the most, actually maybe I'll move over here. The single most important piece of progress from all of this work about quantum information in AdS CFT. So if you're a holographer and you don't care at all about entanglement entropies, and maybe you don't even care about the black hole information paradox, and maybe you just care about AdS CFT itself, you should still care about this statement, which is that the entanglement wedge is the bulk dual of D of A. Okay, and what does that mean? So this is called subregion duality. And it extends our notion of AdS CFT, to bits and pieces of space-times. Okay? So it says that I have the right to delete the rest of the space-time and leave only the entanglement wedge of A, which is going to be bounded by the domain of A, and that is going to be a legitimate AdS CFT duality. Okay? So you can already see that I'm doing this. I'm doing this. I'm assuming, I'm working at a semi-classical level in the bulk, and I'm assuming there's some sort of bulk locality. So otherwise, I mean, all of this stuff, although we can talk about quantum corrections, all of the quantum corrections I'll talk about are still semi-classical. So they still assume, you know, the existence of a well-defined bulk, maybe with some quantum fields living on it, but I can talk about, I have a meaningful notion of this part of the space-time, and you know, so that's so. But anyway, at the semi-classical level, this is supposed to be the case.
So this is at large N and large lambda.
Right, right. In fact, yeah, I was going to say this actually. Thank you. Right, so I think I'll put it here because it sort of belongs here. How much of all this depends on large lambda versus large n? Yeah, so when I said this, I meant large lambda and large n, but then I think there's a very, you know, interesting question of, well, can I relax one of those? I mean, in particular, to my mind, well, what would be most sensible would be to ask, can we relax, for example, large lambda, right? Let's stay at large n, right? Let's not have some crazy fluctuating bulk geometry. Let's stay at large n, but let's say we have actual strings living in there and everything. So we're doing, you know, we're doing classical or semi-classical physics, but we're doing string theory, and then, you know, is there a version of Ryutake Yanagi or HRT or whatever that's valid at finite lambda? So that I think is one of the...
People say something like for Wilson loops, people had this sort of semi-classical world sheet, but some analog of that but all those are very heuristic. You compute, you kind of do I guess for higher dimensions, even the sum over such surfaces doesn't really make much sense, I suppose.
I mean, for Wilson loops, you know, we know how that formula comes about from, you know, a saddle point.
Yeah.
And then you can do perturbation theory about a saddle point. You can include other saddle points and so on. And you know, definitely we can do some of that for the 1 over n corrections, including non-perturbative 1 over n corrections. But so far, no one has, as far as I know, really done much for the, you know, so 1 over lambda corrections have been studied. I mean, you know the corrections to this formula if you have some
square.
You know, yeah. But, I mean, more interesting would be like at finite lambda.
But let's say that somebody finds a formula for finite lambda, something about the world sheet of the string or something like that, let's say. For Ryutake Yanagi, it still seems that this entanglement wedge reconstruction would have to change its nature, right?
Yeah. Yeah. I mean, that's, you know, but what happens to it?
Right.
I mean, it's, you know, maybe you just give it up entirely, but to me that seems a little bit strange because why would you suddenly no longer have a bulk dual? You know, the field theory on this causal diamond, you know, is still well defined. And so it seems strange to me that if you're in a regime where you would expect to have, let's say, a string dual for the full theory, why wouldn't you have a string dual for this You know, the boundary quantum field theory is still perfectly local. This is still perfectly well defined and so on. So, you know, so it, you know, but on the other hand, I mean, I don't really have any kind of concrete proposal, but I think, you know.
Yeah, and may still be associated with some particular set of degrees of freedom, but there may not be an easy way of associating them with a particular region in the bulk.
Yeah. I mean, there won't even be a bulk
Region
per se. Yeah, actually, so let me say a little bit more about this, and then I'll come back to the string theory thing, because I think there's a subtlety here that hasn't really been faced. Okay, so, but I want to emphasize that in the limit in which we're working, this is a sharp statement. And it says that every observable in EA can be written in terms of operators on D of A, which is the same as on A. Oh, because, you know, by the Heisenberg equation of motion, the set of operators on D of A is the same as the set of operators on A.
Now, what do you mean by every observable in EA?
Right, so we are working in a setting where we have where our state is well described by a single classical geometry with quantum fields propagating on it, including potentially the gravitational field. But we're treating the gravitational field as a quantum field, and any back reaction we might have due to excitations is small, so that we still have a well-defined notion of this region. And then the observables I'm talking about are, you know, anything you can measure basically, you know, within this.
So could I word the statement as saying that it is possible to find a definition of local fields inside EA made entirely out of the operators in EA? And then they'll obey all the properties that you want of local fields in the bulk.
Say again, what is the difference there from the way I said it?
I mean, I don't have an a priori notion of what an observable in EA is. At least I don't understand what that means. But what I understood is that you're saying that I will be able to give you a map, give you some formula which says that I will construct a bulk field in terms of boundary fields.
Yeah.
I'll give you a formula. That formula will only depend on the boundary fields in DA, and that formula will have all the properties that you would expect of classical bulk fields. They would commute at space-like distances and so on. And obey.
Well, I think I would want to say a little. I mean, you can say, like, if you know the stress tensor at this particular point in the bulk.
Stress tensor in the bulk. What is that?
The matter stress tensor
Matter stress
in the
tensor,
bulk.
okay.
You know, I think that's an observable from a bulk viewpoint, and I can write that in terms of the operators on A.
Okay.
So I think we want to actually be able. I mean, I'm not sure that there's a real difference compared to what you said. Okay, so this claim. Okay, so I don't know what. So
in particular, you'll reconstruct the metric of that region in the bulk. The metric of that bulk metric will in particular be determined entirely by the fields here.
But I mean, this kind of this reconstruction kind of assumes you know the metric.
Yeah, I thought that was how this HKLL type of.
Well, okay, so HKL is an example of this kind of thing.
Yeah.
But something that's very important here is that this goes beyond HKLL. So the kinds of reconstructions that you can do using HKLL, You can do that and more using this kind of
Python
reconstruction.
sludge, that stuff.
Well, no, that's yet another level of sophistication that I'm not at. I mean, there's much more pedestrian versions of this. So HKLL is for the simple case where you have all the symmetries you could want. You're in the vacuum, and A is a spherical region, and therefore what you basically have is a Rindler wedge. Okay, so you've got all of your isometries and everything, and then there's a formula for writing this in terms of boundary data. But this is much more general. What?
That also assumes the metric in some sense.
Yeah, absolutely.
I mean, you write the Green's functions, some bulk to boundary Green's functions.
Yes. But
Everything is like that. I mean, with this reconstruction.
I mean, I think let's see. How do I want to say it? Okay, so I think Shiraz is right in the following sense that if I gave you do I want to say this? No, I think I'm gonna. It's a good question. I think I'm gonna back off of this because I think that the relation, just as in HKL, the relation between the bulk and the boundary fields, depends on the metric. So you wouldn't know which combination of boundary fields is the metric at some given point if you didn't already know the geometry here.
I don't know. You have normalized the coefficient of the normalizable modes on the boundary.
Yeah.
Then I can solve the gravity equations from there and go and get the bulk.
Well, but the problem is that as you do that, so I mean that works. That's what HKL will do.
Okay.
Right. But at some point you'll need stuff that's outside of. The problem is you may need stuff that's outside of A or the domain of A.
Oh, so it's not determined by what's in A. You say.
Well, I'm saying that the question is, do you or do you not need, when you do what you're saying, stuff outside of A? And my claim is, if the point where you're trying to reconstruct is inside E of A,
then you will not.
don't need things outside of.
Right. So sorry to be so disruptive, but suppose we're at a point inside A, which will only be self-consistent once we determine what the geometry is.
Yes.
Okay. But I take my coefficient of normalizable modes,
Yes.
and as a differential equation problem, I solve the bulk as far as I can go.
Yes. You will not reach all, in a generic situation, by doing that, you will not reach all of E of A.
Differential equation needs to know the
Equations of motion, yes.
but the metric, background.
No, we determine the metric as well, right? This is Einstein's equations.
Yeah.
So we've got two pieces of data because we've got the non-normalizable mode and the normalizable mode, and we can evolve. This is Graham-Pfefferman, right?
But there's a limit to how far you can go.
I agree. So you get some region, and you say you can't get all of it this way.
You cannot get all of E of A this way.
This is what's called the causal wedge.
Well,
Okay,
so actually what's not, what I think I know is that the procedure you're saying, which is HKLL, works in this Rindler case. It is normally assumed in the literature, but I haven't seen this written down, that it works in a more general causal wedge. Okay? So I'm actually not sure about the status of that, but it certainly does not cover all of E of A.
Okay, because sometimes the entanglement wedge is larger than the causal.
Yes, yes. Okay, so let me, for those, define the causal wedge. So the causal wedge, C of A, is the set of points, the set of bulk points in past and future causal contact. Okay, so the difference, is, so let's say this is E of A, and then typically what will happen is that my entanglement wedge will look something like this, and the causal wedge will look something like this. So this is C of A. Okay, in a generic situation. Let me give you a precise example so you believe me that these are typically, generically not the same thing. Okay? So if I have, say, an AdS3 in the vacuum, my region A consists of 2 boundary intervals on a slice. Okay, so this is, A is actually the union of these 2 intervals. Then it can happen that the minimal surface, the HRT surface, joins these 2. And then my causal wedge is everything in here, okay? Whereas the entanglement wedge is everything in here. Whereas the causal wedge will be bounded by these things. So the causal wedge is just this. Whereas, the entanglement wedge is everything in here.
Does the causal wedge equal the other saddle point for the...
In this particular case, it does. Yeah. But that's because I have so much symmetry that it didn't have, there weren't very many options for it. There aren't very many surfaces you can make. So, in this particular case, HKLL will tell you how to write some operator sitting here in terms of the operators in A, and actually it'll only use the operators on this side. And you will not be able to write this operator in terms of the operators in A, whereas subregion duality says that you can.
So now you say, so therefore you cannot even know the geometry outside. Or you, sorry, I missed the punchline. So suppose we're in the second cross that you have.
Mm-hmm. This one?
Yes. And so now the geometry there presumably is determined by things other than in A and A, other than those 2 regions.
No, this is the entanglement wedge.
Okay.
Okay. So this you can reconstruct from A by subregion duality, but not by HKLL.
But I'm wondering how that's consistent, given that stuff from outside can come and hit it. Or is that not true?
So that depends stuff outside where? Okay.
Outside, sorry, I send something from, I change the state in something that is not either the top or the bottom of A.
Well, it depends what time you're doing that. So
I see.
Yeah, but you're absolutely right. Okay, so this claim raises a whole bunch of questions of the type that Shiraz is asking. Okay, all right. So this leads us.
If I understand right, you're going to say that if you change it outside A early enough so that it can affect this bulk point, it will also affect the state in A.
Yes.
I understand.
Yes. So, consistency of the HRT formula and subregion duality in this form, and I mean this is also sometimes called entanglement wedge reconstruction. Is far from clear. Well, I should say consistency with what? Well, actually, let me not. Yeah. Consistency with things you would want. First of all, as I said, M of A exists. The entanglement wedge of A equals the entanglement wedge of A prime. Then there's the fact that if it's true that any operator in here can be written in terms of the operators here, then things that I do at other points, like let's say I have some other region over here, and I do something here, which actually changes things in the bulk, like I have an injection of energy or something. If this point is causally separated from d of a, then it should not change the expectation value. Whether I do this or I don't do it shouldn't change the expectation value at a point here. Okay? And so that means in particular, this whole thing, so let me say it this way. Well, actually, there's something even earlier. Wait, let me say something first. So one thing that has been implicit in all of these pictures, but that I didn't say, but is required for consistency, is that the boundary of the entanglement wedge intersected with, the boundary of the theory is equal to d of a. So if I claim that the entanglement wedge of A is the bulk dual of d of a, well, its asymptotic boundary should be d of a. Okay? Then there's this causality constraint, which says that E of A should be out of causal contact with any point on the boundary that's out of causal contact with D of A. And I can say that in a slightly less convoluted way by saying basically E of A contains C of A. If you think about it, you realize, because it's the causal wedge that controls who's in bulk causal contact, and then essentially that causality condition will be fine as long as the entanglement wedge contains the causal wedge. So this is called causal wedge inclusion. Another thing that you need for consistency is that if I expand my bulk region, if I expand my boundary region, I should not shrink my bulk region, right? The number of operators in the bulk that I can reconstruct from a given boundary piece should only increase if I increase the size of my, so if I, if I, for example here, if I delete this part of A, and then I ask what is the entanglement wedge of the remaining part, it should not extend outside of where the entanglement wedge of the full thing was originally, okay? So this is, so the entanglement wedge of AB has to contain the entanglement wedge of A. This is called nesting, or inclusion monotonicity. There's another one, which is that S, so far I'm just talking about properties of the entanglement wedge, but also as an entanglement entropy, S of A has to obey a whole bunch of properties. Probably the most important one, there are others, but is this strong subadditivity. Which is this, so if I have, yeah, let me just write it. So this is where A, B, and C are disjoint regions on a common boundary Cauchy slice.
Sorry, but if A prime is the complement of A
On a Cauchy slice?
on the boundary, yeah.
Mm-hmm.
Then is the entanglement wedge of A prime the complement of the entanglement wedge of A?
If the whole thing is in a pure state.
Yes,
if there isn't some black hole or something,
yeah, let's suppose.
then yes. Yeah.
Okay. Then I think I understand why 4 is.
This is equivalent to what you were saying?
Yes.
Yeah.
Because we wanted the causal part of A prime not to intersect the entanglement wedge of A. And then that is guaranteed by this.
Exactly.
Yes. Okay.
Okay. And I'm not done yet, because the entropy obeys not just this, but as you all know, certain other equalities, for example, the first law. So what happens if I change my state a little bit, the entropy changes a little bit, and that's related by the first law to the change in the energy. In this case, the energy is the modular energy, so I'll define that. But let me first write it. So for a small change in the state, and now, by the way, okay, these changes I'm talking about now, they're small, but they're big enough to include back reaction. So I'm actually talking about an honest change in the geometry, in the metric. The change in the modular Hamiltonian, which I'll define in a second, has to be equal to the change in the entropy. So K rho is minus log rho. Sorry, this is A. Sorry. This is the modular Hamiltonian. Okay, and this is straightforward to derive from the definition of the von Neumann entropy. So here what's going on is I have a certain state rho, which I'm going to change. So now I have a state rho plus delta rho. Okay, so I'm changing rho to rho plus delta rho. And as a result, the expectation, so when I do that, I don't change my modular Hamiltonian. So this modular Hamiltonian is defined as minus the log of my original rho. But of course, since my state changed, the expectation value of that operator changes. And also, of course, my entropy changes. Okay? Okay, this is a rather long list of consistency conditions. So you see that the correctness of this formula and this claim is by no means guaranteed. I mean, if somebody claims to have a formula for the entropy or some form of subregion duality, you know, they have a long list of criteria to check, okay? And the thing which I think is quite striking is that, okay, so first of all, let me say that this formula can to some extent be derived from first principles via path integral calculation. However, that derivation, because it involves manipulations of various gravitational path integrals, you know, is subject, requires a certain amount of faith. Okay, and it involves certain analytic continuations and hoping that certain complications don't arise, and if you proceed by brute force and you assume everything is going to be nice, you land up on this formula.
Even at the classical level?
Yeah, at the classical level and including the corrections.
What I mean is you feel that the argument was not watertight even classically.
Oh, the argument was not watertight even classically, yeah. This claim, that claim, the subregion duality or entanglement wedge reconstruction, actually hinges on what happens here because it's a statement about the quantum operators in the entanglement wedge. Okay, so you have to know, you can't derive entanglement wedge reconstruction just from the classical piece because the classical piece doesn't even know that there's quantum mechanics, okay? And I can go through those if people want. But having said that, so you could take the attitude that, well, we derived these, therefore it's true, therefore there's no need to check these. That's, you know, that's one point of view. But I think it's, even if you think that, I think it's still interesting to see how it does it, right? And I think the most interesting thing is that all of these depend on knowing the gravitational dynamics. So these fail if you do not use the Einstein equation in the bulk, okay? So they follow from and actually can be used conversely to derive the Einstein equation, okay? So
are you saying that any higher derivative corrections to the gravity violates one of those properties?
No, but what happens is that the formula itself changes. So they would, if for some reason you changed your bulk theory and didn't change the formula, then you would violate these properties.
I see.
Okay. So, but for now I'm working in the case where you have Einstein gravity in the bulk. Okay, proving any of these requires not just the Einstein equation. So Einstein equation, knowing something about the matter. The easiest thing is the null energy condition in the bulk, which says that T mu nu K mu is non-negative for any null vector K mu, and asymptotically AdS. Boundary conditions. And conversely, if you make enough assumptions, you can go the other way. So if you assume the HRT formula and you assume asymptotically AdS boundary conditions, then the first law implies the Einstein equation.
But if I assume the HRT formula is sort of like a boundary term for, I mean, the Wald formula, there's a one-to-one map between Lagrangians and Wald entropies, right? Because I take the Lagrangian and I differentiate it with. So if I know the HRT formula or the analog, I know the Lagrangian, and so I know the equation.
Yeah, I mean, this is what Wald did is he said, well, if I have some equations and I want the first law to be true, what do I get for my entropy formula?
Good.
And this is just essentially running that argument backwards.
I'm saying you don't need to do first law and so on. I mean,
No,
okay, first law.
First law.
Fine, first law. First law, but even for black holes, right?
Yeah, I mean, black holes are just a special case of all of this. So.
Right.
But yes, I mean, logically, it's very closely related to what Wald did.
Right.
Yeah, absolutely.
I'm saying just at the level of equations, Wald entropy is some derivative of the Lagrangian.
Yes.
So if I give you the Wald entropy and you want the Lagrangian, it's a matter of integrating. Right?
Well, if you know that, I mean,
if you know that, I agree.
I mean, this is sort of, taking a more abstract approach. I mean, in some sense. I mean, of course, secretly that's what's going on, but,
Right, fine, thank you.
So there are some constraints to higher derivative correction to Einstein gravity from causality.
Yeah.
Can you kind of derive similar constraints by imposing those conditions?
I think one should be able to, but I don't know if that's been done. I mean, I think, for example, if you look at number 4, causal wedge inclusion, there are many circumstances where it's just on the border of being violated, where in Einstein gravity, the causal wedge coincides with the entanglement wedge. And so then you would worry, well, if I add something with the wrong sign to my Lagrangian, is it going to go the wrong way? But I don't know if that's been done.
Okay.
Yeah.
I see.
Okay, so, and let me just complete this story by, I probably won't go through the logic of how these things are related unless people want me to, but it should be said that, so at first order, from quantum corrections, what you get is the entropy, is basically the bulk entropy, or I could just say this, the entropy of the entanglement wedge. Or let me write it this way. So this thing is the bulk. This thing is the entropy of the fields on R sub A. That's the first order correction. There's more corrections.
I sometimes hear people saying that this is true to all orders in 1 over n.
Okay, so let me tell you what is thought to be true to all orders in 1 over n. It's not this. It's, the only thing left is S of A. Okay, so S gen of a given region R, let me just do this, is defined to be the area of the boundary of R over 4 G Newton, where this is just, I don't know how to write it, let me write. It's the bulk part of the boundary of R, so let me, so this is some R, and this is the bulk part of the boundary of R, plus S of R. It's a generalized entropy. This is the thing which is supposed to increase according to the generalized second law, even when a black hole evaporates, etc. And then what you do is you minimize and extremize over all choices of R such that the boundary part of the boundary of R is A. So you do what we were doing before for the HRT formula, namely before we were just finding the extremal surfaces and then minimizing if there's more than one. Now we're finding the surfaces which extremize the generalized entropy and taking the smallest if there's more than one. And this is called the quantum extremal surface formula.
That SR includes the entanglement entropy of all fields, including the graviton?
Yeah, so you have to be a little bit careful. So in principle, yes. But you have to gauge fix in a certain way because there's a danger that the graviton actually, like how do you define a given surface if you're allowing perturbations of the metric? And there's other subtleties which honestly I don't really understand very well in defining this thing. But I guess maybe one thing, right, so you can ask whether this is sort of a well-defined quantity. In particular, you know that this is going to be UV divergent precisely on the surface here, on this d bulk R. So there's going to be a bulk UV divergence here. And of course you have to have a regulator, and then this answer will actually depend very much on your regulator, and then what's supposed to save you is that, well, as a function of your regulator, so first of all, the divergence is just proportional to the area, and the Newton constant gets renormalized as a function of your cutoff also, such that the total is supposed to be independent of the cutoff. Now, I think there are good reasons to believe that that holds at least like after you extremize. It's not entirely clear to me that this is true for, if I just have a random surface, that this delicate cancellation will hold. Because Yeah, I mean, if you're really careful about it, there's subleading terms here, and there's subleading divergences here, and all of that stuff is supposed to, be completely self-consistent.
And this integral over the gravitons, effectively it means that we're integrating over a fluctuating surface R. So instead of extremizing, are we doing it somehow a path integral because of the S of R over surfaces?
Well, in the end, this is supposed to, pick out a particular surface. Once you do the extremization, this is supposed to pick out a particular surface.
Isn't it strange that we're working to all orders in 1 over n and there's no fuzziness about the surface?
Yeah, this is one of those things that I've never completely understood. I think an expert might have a good answer for you.
Wouldn't it be sorry, knowing nothing. Classically you extremize something, quantum mechanically you do a path integral. That's what I would have expected. And even over the surface.
Right.
Why is this supposed to be true for all orders in 1 over n? I thought, isn't it sort of more or less like the classical in one loop, or?
So when you, no, so this is not just supposed to be one loop. This is supposed to be, if you're powerful enough to calculate, the full entropy of your quantum fields in this region, then that's what you're supposed to include here. Okay? I mean, you could even, as we discussed in someone's talk, the bulk matter could be a strongly coupled CFT, and then you should just go ahead and you should calculate, the entropy of this however you can, and, and then go ahead and do your extremization.
If the bulk matter is strongly coupled and we're doing one particular order in 1 over n, that sounds totally reasonable to me. It's the all orders in 1 over n that seems strange.
Well, if the bulk is strongly coupled,
You could have the bulk very strongly coupled and gravity weak.
Yeah.
And then that's fine, right? That's just the bulk loops, that's okay. But it's the gravity fluctuation that seems...
I mean, if the bulk matter is strongly coupled, then there's no notion of one loop or whatever of this.
No,
you have to calculate some other way.
No notion of one loop or whatever in the bulk matter.
Yeah.
And that sounds totally reasonable.
Yeah. It's about the G Newton.
The G Newton.
Yeah. I mean, so there's a derivation of this, by a replica trick in path integral, where what you do is you use the effective action, the quantum effective action that you derive from your bulk matter as a function of the bulk metric. Okay, so you basically integrate out all of your matter, and then you treat which is somehow supposed to include the metric perturbations. And then you're supposed to, as normally with the quantum effective action, you do classical mechanics with the quantum effective action. And that's the spirit of this thing. I don't know, you tell me if this is it kosher? I mean, but there's a huge body of work before entanglement entropy that was just about the generalized entropy. And, so people have been working with it, in the black hole context for decades. I mean, that doesn't mean that that everything is necessarily well defined, but I think these issues have been thought through. I just personally don't really understand them. But if you see a reason why it shouldn't make sense, I would love to hear that.
Are you going to say that entanglement wedge reconstruction works for a particular surface to all orders in 1 over n? That's starting to sound crazy to me. Because the surface should also...
I don't understand why you're more bothered by to all orders in 1 over n than to first order in 1 over n.
Okay, it just sounds better to say it too. I mean, maybe there's something special about the first order.
Well, okay, to be honest, actually...
There's some fluctuation.
There is something special about to first order, which is that, so in the formula, so there is something different about this formula than this one. So this was, so let's go back to, okay, let's go back to this. This thing is the HRT surface, the classical HRT surface. And this thing is the classical entanglement wedge, okay? Because this, by definition, extremizes the area,
So you don't have to.
you don't have to move it,
Yeah.
right? If you want the first order perturbation, you don't have to move it. So in that sense, this is better defined than this, okay? Another thing I'll say about this is that there are counterexamples. So there are situations where you play careful games with the state of the bulk matter. Nothing like exotic or impossible, but you just, tune the bulk matter in some way so that this thing this one is actually wrong, not just, and it's not just wrong by like some very subleading thing, but it's wrong already at order 1. In other words, it's wrong already, at this order. Okay, so it's possible to, this thing is at most only true subject to some assumptions about the bulk quantum state. That the bulk quantum state is, has some kind of reasonable entanglement spectrum, essentially. Is the kind of state that you would normally get from a quantum field theory somehow. I mean, without, I'm not being very specific, but this thing has some finite regime of validity past which it's just not true anymore.
Are the arguments for this formula entirely formal, or have people tried to do serious calculations? I'm worrying about the 1 over n. The other thing sounds completely.
You're just this.
Yeah, just let's say I go to second or third order and 1 over n.
The situations where, see, it's this and this don't just differ by the fact that this includes higher order and 1 over n. They differ in something more specific, more dramatic, which is that you actually change your definition,
What you extremize changes.
Yes. And that is the thing that gives rise to the whole island story.
Right.
So that's the situation where you see a dramatic effect and you need this, you cannot use this. And the dramatic effect that you see is matching up with something you thought was true for some other reason.
Actually, for the island story, I mean, what you need for the island story seems correct to me. But I just think the statement of it as stated sounds a bit funny.
I mean, I'm not quite sure what I should do is sit down and like really try to study it, but can I just make an appeal to authority? I mean,
Is that Maldacena?
No, I mean actually it's Aaron Wall who has spent a huge amount of time thinking about the the expansion in powers of G Newton of the gravitational effective action, and has no trouble at all manipulating things like this. And he's a smart guy. Okay, that's a terrible argument. But at least it was not done out of sloppiness.
I understand.
So he derived the second formula, or this? Which of...
Okay, so this... This is the quantum extremal surface formula. This one, by the way, if you care about names, this is Faulkner, Lefkowitz, Maldacena formula. So this one was Engelhard and Wall. Although they were they were dumb enough to give it a name so people don't call it by their names. So which is too bad because it's like entanglement wedge, but so people call it the quantum extremal surface formula. And by the way, it's not easy to study all of these things, but it seems to obey 1 through 7. I mean,
You mean either formula or
what?
both formulas obey 1 to 7 or?
Okay, I meant the quantum extremal surface formula. This one, there's less to check because this is necessarily small compared to this. You can check, for example, strong subadditivity, but that kind of follows from the fact that like this thing has to obey strong subadditivity because it's a quantum entropy, and stuff like that. I'm trying to think whether, I mean, number 7 is probably the one that's most, where you would be most sensitive to, yeah.
But just to get it straight, the island formula relies on the quantum extremal surface and doesn't work for the...
Right. Right. The island one.
So now the claim is that the first one is right and the second one isn't? Or?
No, well, right, yes. I mean, in an extreme situation like that. So this is only supposed to be true when your state is, basically when your 1 over n expansion is under control.
When SR of A is much smaller than the other guy.
Yeah, when this is only supposed to be true when this is small compared to this, and hopefully other terms are even smaller and so on. So in the island case, you've intentionally put yourself into a situation where you've waited long enough that your 1 over n corrections have grown to be the same size as your order 1 thing, and then, then of course, this is not a legitimate thing anymore. By the way, let me just say one thing. I mean, I don't know, this, modulo these issues of like, what do you do with the gravitons? This is a very reasonable looking formula, and I think this is also a reasonable looking formula. Let me give a heuristic derivation of this, which also I think maybe to some extent points out its limitations. So the derivation goes like this. You're interested in calculating the entropy of, in some state, and there's like some dust which is entropic, or maybe it's entangled, and so on and so forth, and you want to take into account of that. Okay, fine. So, and then you realize, you take out your microscope and you look at these pieces of dust, and you realize actually they're tiny black holes, And then you say, oh, since they're black holes, it's classical. I should just use my HRT formula. And the thing you're going to end up is what you would have gotten had you not realized that these pieces of dust were black holes, and you would use this formula, right? So, now, but you see that, of course, black holes have a very particular kind of entropy, because they're thermal states, right? So if you give me if my dust was entangled with other pieces of dust in some much more complicated way, then maybe this is not true, right? Okay,
But just before we go on, the arguments for this have been entirely formal, or people have done serious, particular case calculations.
I don't know if you're going to like this. People have done particular case calculations in bottom-up scenarios, especially, double holography. So double holography is another case where you can really go to town because you're basically, I mean, it's almost obvious that this is going to work in a double holography setting because it's just going to equal the classical HRT formula in your second level of holography. Okay, so I don't know, does that count? I mean, that's maybe you just put the answer in by hand by declaring it's, double holography. Other than that, and islands,
just an ADS5 to 2 loops in gravity or something. I mean,
you cannot calculate the left-hand side. You have no other way to calculate the left-hand side.
Right. But just to see that the right-hand side is well defined. that there's no problem when you go ahead and try to calculate it. Nobody's tried to do that. Seriously.
Oh, I doubt it, but
Yeah.
you know, there may actually the place. So, if I was planning to do that sort of thing, I would do it in the ADS3 setting. So this formula has actually been checked quantitatively in ADS3, where you have a way to calculate the left-hand side independently.
And you also have no gravitons, right?
That's true. Oh, so you're worried about the gravitons.
Yeah.
I doubt that anyone has done that. Yeah.
Right.
Yeah, I mean, yeah. This one is definitely not on the same footing. I think it's probably true, but I think that there are some assumptions about when it's true, and we really don't understand what those are. Right. So, so just to mention a few other things that, you know, so this immediately leads to, yeah, so other things that this leads to, right. So, so I mean, I think the thing which is, you know, most interesting about this is, you know, it tells you that there are parts of the bulk not in causal contact with the part of the boundary that nonetheless are encoded by it. So it means that, for example, black hole interiors are encoded, you know, on the boundary, you know, which you know, from some point of view, it's, if you believe AdS CFT, it has to be true, because if you have the whole boundary, you have to have the whole bulk. Unless you don't believe that the black hole interior actually exists, there's a firewall. So this is like you know, can be thought of as an argument against firewalls. I was going to say something else about this. I lost it.
Sorry,
Yeah.
Suppose I have a black hole, the entanglement wedge of the whole boundary, that goes through?
Right. So, so if you have, let's say you have an AdS Schwarzschild black hole, in this case, I mean, there's a lot of symmetry, and the entanglement wedge of one side is the exterior region. So this is E of A, E. It's also C of A. The entanglement wedge of the whole, both boundaries together is the whole thing. But you see the causal wedge doesn't include this part and this part, right? So, you know, there are parts, and in fact, there can be parts, I guess I erased it, but there can be parts of the bulk in a more complicated state, like if you start throwing matter in, there can be things in the middle that are completely out of causal contact to the future and the past with both boundaries.
Because it's expanded like that.
Yeah, and yet some points in here will actually be included in the entanglement wedge of one side. Other points will not be included in the entanglement wedge of one side, but they'll be included in the entanglement wedge of the whole boundary.
And sorry, if you had a black hole formed by collapse, in that case,
then the whole interior is contained in, so this is R equals 0, this is my horizon, and the entanglement wedge of the whole boundary is the whole bulk, including this, but the causal wedge excludes this. Okay. So that's one implication. Another implication of this is this quantum error correction. So, the bulk. Well, let me try to be more specific. The bulk fields define a quantum error correcting code. Okay, so what that means is, so as an example, if I divide my boundary into 3 regions, then each of them has their own entanglement wedge. So I have, entanglement wedge of A and so on. But then you can ask, well, who does this region belong to? So an observable in this point cannot be reconstructed if you know A, or if you know B, or if you know C. But if you happen to know any 2 out of 3, then you can. So this point is contained in the entanglement wedge of AB, because the entanglement wedge of AB is this whole region, which includes both of these and this. So that may not seem, that's essentially the same phenomenon as I was saying, that these points here are not contained in the entanglement wedge of A, or if we call this B, or B, but they are contained in the entanglement wedge of A union B. But here it's even a little bit maybe more dramatic, because while it's contained in the entanglement wedge of A union B, it's also contained in the entanglement wedge, so let me call this X. So X is contained in this. It's also contained in the entanglement wedge of A union C and B union C. Which means that you can throw away any one of these 3 and still be able to recover X, an operator at X. And that's what a quantum error correcting code does for you. It makes it so that you can lose, if you have 3 qubits, you can flush any one of them down the toilet and still recover the state that's encoded. Okay? Now, what's not entirely clear to me here is whether there's more going on than what we would have normally called holographic RG. So I think this is definitely closely related to holographic RG. It may just be sort of a refinement. So I think there's a sense in which any RG is kind of like an error correcting code, in which the low energy states are your code subspace. And with holographic RG, we know that going deeper into the bulk is representing, lower and lower energy sector of your field theory. And so this may just be a kind of a sharp statement of holographic RG. Right, and then you get to, oh yes, okay. Another implication of this story.
Sorry, Matt. One.
Yeah.
In the case, if I actually wanted to I want to know what the geometry is inside my entanglement wedge.
Yeah.
Knowing what I have in the field theory here, what do I actually do? To get to the causal wedge, I understand you use the equations of motion. But how do I actually find the geometry outside?
I don't know. I mean, I don't think, I don't think it's going to be very straightforward. I mean, even, there's an easier problem, which is still very hard, which is just any point, so not reconstructing the geometry, but just reconstructing a point outside the causal wedge, but inside the entanglement wedge.
Right.
Like here. And I mean, there are,
Part of that statement is reconstructing the geometry, because unless I have the geometry, I don't even know what I mean by the point.
No, but I'm saying that, even if I gave you the geometry.
Yes.
So what I want to say is that there are formulas for these things in principle. And there's some complicated, because this is, once you say it's an error correcting code, then you have the machinery of quantum error correction to use, and there are these things called PETS maps. I don't really understand these very well, that you can use in an error correcting context to sort of reconstruct your original state. But it's all like kind of formal, and so
In that case, can't I build a Cauchy surface in the bulk and then use equations of motion?
yeah, in that, well, I guess, I mean, that's probably not the best example because it's on the boundary. I mean, I think technically, somebody could object and say no, because actually these don't cover that. There's a point they're missing, which is kind of like, the Poincare patch. If I say that the Poincare patch is dual to the Minkowski space on the boundary, I mean, which was, when I was growing up, that was what people said. So, how come you can't just use the equations of motion? Well, because there's one point missing. Here, there's one point missing. But if you don't like, I mean, examples like that are kind of irritating, so, but I think, how about this example? Then you couldn't do what you had said, right? Right.
Sorry, so the final thing there was that it should be possible, but some very complicated thing.
Right. Oh, this is what I was going to say. Yes. Excellent. This is where the Python's lunch comes in. I think that, let's see, do I want to say this?
Just some analytic continuation would work. You build
Well,
this,
if you have analyticity, of course. I mean, but that's cheating, right?
build the metric in this region, and since it can't be affected by things you do outside, somehow feels you should just be able to do differential equations. I mean, in a differential equation sense, anything you did in A prime can't affect the answer.
Yeah.
So it feels you should just, from differential equations, be able to get the answer somehow.
Okay, I mean, your intuition may be correct, and it may just be that it sort of hasn't been, like, said in the right way, so that becomes clear. But there are definitely cases where that's not going to work.
Okay.
And those are the Python's lunch cases, where there's some other extremal surface which is getting in the way, and then, somehow there's not enough room for your information to get through, and then it's believed to be a, exponentially complicated reconstruction, etc. So your intuition may be correct. The thing is that I didn't go through it, but the argument that leads, something to know is that this claim of subregion duality is derived, only from this one formula, which is kind of